In video number 25 of the Foundations of Computational Economics course, we will be coding up a hybrid algorithm that combines the elements of Newton-Raphson method with the bisection, so it will work with bounds. This is an example of a hybrid algorithm which is built on a deeper merge than the poly algorithm I talked about in the previous video, where we would have two stages and use, robust but slow method in the first stage to find a nice starting value for the fast and accurate method in the second stage that converges to the actual solution. So here we will have sort of like a deeper merge of the two algorithms, which is also possible, and I think in this case it works really well. So the motivating example is this equation here, and this equation we came across in one of the applications in I/O with discrete choice. So this was part of calculating the best response function for one of the competitors in the dynamic game of two players. Well, it's actually in the mixed strategy equilibrium. Okay. The important point is that we can see in this equation we have both log of x and log of 1 minus x that constrains immediately x to be in the open interval between 0 and 1. And so this strong restriction is the first really complicated part about this equation, because any algorithm would break if it happens to step out of this interval of between 0 and 1. And yet, there is exactly one solution for any values of A, B, and C, and that we can see from the following argument. So assume without loss of generality that A is greater than 0 and B is less than 0. We have to have the condition that the signs of A and B are different. Okay, let's see. So f of x is continuous in the domain between 0 and 1. Is it true? Yeah, well, logs are continuous, and then this is a linear combination of logs. The f prime, which can be expressed as a over x plus b over y minus x. So f prime is actually greater or equal to 0. It's strictly greater than 0 for all of the admissible x's under our assumption here, or it is strictly less than 0 under the opposite signs of a and b. So in any case, the function is strictly monotone. And also, you can see that if x approaches 0 from where it can approach from the right, then f of x approaches minus infinity. Well, that's because of the log. And on the other side of the interval, as x approaches 1, then the f of x approaches plus infinity. Because b is greater than less than 0. So in other words, what we have is that the function in question is crossing 0 at only one point on the admissible interval. So the solution should be easy to, or shouldn't be hard to find, right? We already know so much about the theoretical properties of this equation. And yet, because depending on the value of c, the solution can be arbitrarily close to either 0 or 1. C is just a constant that moves this whole function up and down. But it can also move the solution arbitrarily close to the boundaries, which I excluded. And that means that we can easily run into the numerical problems trying to solve this equation. And that's exactly what was going on. So what can go wrong? Well, Newton can overshoot easily and get itself out of the admissible interval. And of course, that's going to be a problem, because then the function cannot be evaluated, let alone the derivative, and the algorithm will halt. Bisections. Well, imagine that the solution is really close to one of the limits of the interval. and we are bisecting that interval. I mean, we know the signs are different on 0 and 1, so bisections are applicable in principle. But if the solution is really close to one of the borders, then it will take forever to converge. Successive approximations, I'm not really sure how to do it here. But here's an idea. The idea is that we can initialize the algorithm as if it was a bisection algorithm, a bisections method. And then we can try to compute a Newton step. But the main idea is here to check whether the Newton step would be within the bounds of the domain of this f of x function. And now, if it is within the bounds, then we can take a Newton step. But if it tries to take ourselves out of the admissible set, then we can switch to bisection step and do a less efficient but more robust step then. And this can iterate until convergence, or a maximum number of iterations, but it is guaranteed to be able to compute the function and the derivatives in each step. And that's the idea. So let's implement this idea. And to start with, we will import NumPy and Matplotlib as always. We may want to draw some pictures. And here also, in NPy, there's the setting for the errors, which we've done a few times already. Here I want to ignore the invalid values for the functions. And that's because we may occasionally call the log of 0 or here and there. So let's just set it up so that we don't get the warnings. All right, and it's time to code up the function. Make the plot of the function, meaning the solver, and make a plot of the. Oh no, it's not the solver; it's the function itself. Okay, let me start with that. So let's call it f, and this is going to be as before a lambda function of x. What do we have? A times np log of x plus b times np log 1 minus x plus c. This is our f of x, and this is what we want to equate to 0. Now, where do the a, b, and c parameters come from? They have to come from somewhere. And let's just initialize them to some values. Well, simplest values, right? So I assume that a and b are not zeros, right? That was the implicit condition over here. And they have to have opposite signs. C can be 0 to start with. Okay, let's make a plot. So the way I usually do it, right, is to set up a grid using linspace in some bounds. Well, bounds are very easy now. They're just between 0 and 1 and some points. And then we can just plot with xt f of xt, say in red color. And plot show. Yeah, PLT it must be. PLT show instead of plot show. Okay, let's make it a little bit more concise. The next step is the solver. So here we are. Let's add the 0 line. So I'm going to just point to 2 points, x of the beginning, y of the beginning, it should be 0, x of the end of the point, and then let's make color gray. Okay, there we are. Let's also write. Let's also make the vertical lines maybe. No, that's okay. Let's see what happens if we change C, but you can see already that what's going to happen is that this line is going to move up and down, and you can see here that the solution, well, if we make a lot of points here, then we'll get the solution. The solution is moving closer and closer to 0, or if signs are changed to 1. The signs of A and B. Now what happens if A and B are not symmetric? Well, this whole curve becomes less symmetric. But the nature of it doesn't change all that much. It's still pretty unpleasant to work with, like this, for example, right? We know that it bends down and goes to -infinity at 1 over here. But because of this asymmetry, or like this, well, this is actually this is better, right? But because of the asymmetry here, the solution, the crossing point with the 0 line, can be really, really close to 1. Let me draw it with even more precision. You can see that this goes down really fast and very close to 1. So I can't really even, by adding grid points on the interval, I can't really plot it make it a plot lower. Okay, so this is the function that we are working with. All right, let's code up a solver, and I should probably go to the normal notebook mode here. And let's make some comments. There's going to be a solver. I'm just going to write everything in sort of plain code first, and then reorganize it a little bit. What's the name for this? Well, let's call it Newton bounded. This is going to be the implementation of Newton algorithm with bounds. Okay. All right. So what's a good place to start this new procedure? Well, we know that it will be combining the Newton and the bisection methods. So let me bring up the code of both of this. And as we saw in the last video, there is now an optim.py module which combines the source of all this solver algorithms that we've coded up in this course. And we can see here's the bisection, here's Newton, and I guess I don't need to see anything else. So first question is, what are the arguments to this function? Well, it must be the combination of the two. So I'll just copy this line here, and I'll copy this line here. So the arguments to the function will be the function, its gradient. We said function, its gradient, the starting point x naught, but it can actually be not given if the interval is given. So the initial interval, tolerance, maximum number of iterations, and the callback as before. Okay, now first I guess we'll need to make a check for the signs of the function, and I'm going to do it in a slightly different way here. There is a function called Sine in the NumPy. I'm a little bit concerned about the value at the bounds, exactly at the bounds, being infinite, especially in our case here. But we only need signs, so signs of plus and minus infinity should be possible to compute. A function is used to indicate the sign of a number element-wise. Well, we'll have only one element here, and so let's call this sine A and sine B, and calculate the sign of the function at A and the sine of the function calculated at b. Sine A and sine B. And now we can assert that SA times SB is strictly less than 0. Right? Sines are represented by 1 and minus 1, so this multiplication is going to be it's going to work. Returns the sine of array. If the array is scalar, then the sine will be scalar. I want to actually know how it converts to an integer. The sine function returns minus 1 and 1. Okay. Right. Here we are. So this is what we've copied. Okay, let's just use this. So f of a, but now we will have SA and SB as sines. So if their product is greater than 0, then there's a value error. The function has the same signs in the bounds, which is an error. Okay, this is what the bisection does before the start of the main loop. Let's copy the main loop from Newton. Oh, and by the way, there's an error here, right? The Newton should return x1. That's the good example of propagating error when you're copying the code. Same thing here. Okay, that's why copying the code is never a good thing to do. A main loop. Main loop is going to go with iteration count I as before. It will go up to max iter, and if max iter is reached, then the else will fire and produce a runtime error failed to converge in so many iterations. Wonderful. Now, this is the Newton step, as we remember. But we will not immediately update the x to the Newton step, and so let's save it to some other variable, newt. And now we want to check whether the Newton step has taken us outside of the interval or not. And so if not the case that newt is between a, I guess it can be less or equal, and b, if it's taken us outside of the interval, then what should we do? Then we should do the bisection step instead. One step that I didn't yet insert here is, see, I'm thinking that x naught is already defined, but it could have been none. So let's update x naught if it is none. So I'm going to use the ternary operator here. What should it be? It should be a plus b over 2. If x naught equals none, else x naught. So remember, this is a nice way to write an if statement for an easy case. Just take in one line. So x naught should be updated to the middle of the interval. If x naught was none to start with, if it wasn't, then it just remains itself. Okay, so what's the bisection step? We need to check whether the sine of the computed, so let's see, sine of the fun of x naught right, is the same as the sine of say a, sine a, and if this is the case, so if the sine of the function at x naught is the same as sine of a, then a should move. Then a should be moved to x naught. Else, it should be b that is moved to x naught. And interestingly, the sine of A will remain here. So I thought I would also write sine A equals something, but it will be the same, right? It's the sine to like the sine of f of x naught. Well, this is not necessary because the signs are the same by this exact condition. So we're moving the boundaries without changing the sign, which is the purpose of the bisection step. So this line is not needed, really. Now, I don't really like this if statement to take so much space. Let's do a similar thing as we did here and use ternary operator. How can we do that? So we have if sine of x equals so a equals x naught if sine of x, else, oh, and here we need to say b equals x naught, right? And that's impossible because with this expression we are changing the a, the value of a. Well, but we can work with tuples, right? We are in Python. A and b should equal x naught and b. So we are making this assignment. So a will be replaced and b will remain the same if sine of f function at x naught is the same as sa. Else, it should be updated to a different value. What's the different value? We're changing a here. Here it should be like this, right? So ab will be assigned to ax naught. Okay, so that completely replaces this 4-line piece of code. One more thing that I don't like is that we're calculating the function of x naught twice. So why don't we pre-compute it? And f naught, for example. We can just say function of x naught, and here it's just going to be f naught. And here it's going to be f naught. See, it hasn't changed. So if Newton's step takes us out, then this function doesn't have to be computed again. Okay, now I think we're good. So this is updated. And what should be the next step in this case? x1. It should be the midpoint between the updated a and b. Like so, right? And else, if the bisection step we didn't have to do, let me just copy this comment as well. This is the bisection step. But if we didn't have to do the bisection step, then x1 can be just set to the Newton, the value, the next step according to Newton's step. Okay? So if we are inside of the interval, or if we're not inside of the interval, then we're doing this branch, and if we're inside of the interval, we're just updating according to Newton. Very well. And this is in complete correspondence to what's been going on here. Oh yeah, and this is using the same logic. So now we've updated the x1. So now we can compare x1 to x naught and calculate the error and do the callback. And if error is less than tolerance, then we can break. But if not, then we get ready for the next iteration by placing x1 into the x naught and then repeating everything again, calculating the function of x naught, which is function of x1 that was never calculated yet, and repeating these things. Now, for the callback, we should add some more information, right? The iteration count is here, the error is here, x naught and x1 is fine. I would like to know what sort of iteration step that we've made. So let me call this type equals, and I want to say either Newton or bisection. How do we know that? So the Newton step is done over here, and I can just say, I just can use a separate variable, a string variable, for example, to say that this was Newton. And over here, we can say bisection. And then the type can be outputted as a step. Now, we probably would also like to keep track of bounds. And we can do that by just passing them as under the name bounds. And since bounds are everywhere, oh no, I'm sorry. So the bounds is A and B, so let's pass them as A and B. The other way to do it was to would be to pass bounds as a tuple. Okay, now is this all? I believe so. I think this should be it. And we return x1 as the latest available iteration. Yeah, it's not going to be much different from the previous one. And of course, the you know, getting ready for the next step, for the next iteration is just as before. X0 should be assigned the value of x1. And so we are ready to solve the equation. How would we do that? X star equals Newton bounded function f. Oh, we need the gradient. So let's add the gradient here. A over x plus b over 1 minus x. Function gradient. A is 0, b is 1. Well, they defaulted to 0, 1, so let's not bother. Tolerance and callback. And let's just print xs. So something's wrong and p is not defined. Well, I thought we ran that one. Too many values to unpack, expected 2. Okay, that's this line here. Too many values to unpack. X naught b, a x naught. Should be 2. Too many values to unpack. No, you don't quite understand. So let's consult the optim.py, which is open over here. And we can see that when we are passing the tuple, we need to include it into the brackets. Otherwise, the logic in the string is broken. So we should have brackets here and here. Okay, and there we are, 0.99534. Okay, what about a large c? 0.999999. Ah, this is pretty close to 1. So that was what I meant by the fact that the algorithm can deal with all these nasty situations. Now it's hard even to print. We know that this function goes down to minus infinity at 1. But the number of grid points that we have here, 1000, is not enough. The distance between the next to last and last is small, right? It's 1000. But this is within this distance that this function here goes down to infinity. And yet we get the solution. Okay, let's look at how the algorithm performs by calling it at different situations and printing out something useful. So let me define a function print either, and it's gonna pass now, and we'll call it callback. We'll give it back as a callback. Okay, so how does this work? Let's just print, and yeah, it should take the arguments. So it's going to take only named arguments, keywords arguments, and let's just print this. Now I want to limit the number of iterations, because there's going to be a lot of prints, to say 3. failed to converge, that's fine, but here are the 3 callbacks. Oh, and let's turn off the plot for now. So here's our three callbacks, bisections. Oh, let's go back to normal. C. Newton bisection, bisection. Okay. Newton bisection, bisection. It's kind of strange that it starts with Newton, then goes into a bisection. What I've seen before would be the opposite succession, but it's interesting. Let's look at this one. So, okay, what I want to say is that this KW args is a dictionary. Okay, it's a dictionary, and so we can unpack its values and print them for just inspecting. So what would you like to print? What would we like to print? Okay, let's say iter equals. Oh, let's use dot format this time. So we want to print the format, the iteration, and I could have said kwargs iter and many other things here. Or I could unpack them and assign to separate variables, which would be easier to name. Let's do the latter. This is going to be iter. So here's my iteration 0, 1, 2. Now I'd like to check one thing here, is whether you can access the dictionary directly. Okay, you can do this in pandas when working with data frames, but apparently you can't do it for any dictionary. Okay, good to know. All right, so now I can just say I here. Iteration, the current x should be given next, and let's unpack that. Now, should we choose? See, there's x0 and x1, so before the step was taken and after the step is taken. Which one? Well, let's take x1, but then maybe if I equals 0, so the first one, then we also print initial x0 equals 1.5f, and this should be I don't want to unpack this. It's going to be just one called once, x not, like that. Okay, x. What else do we want to print? I guess we want to print the error. Error. And we probably want to print the A and B. Okay. Error and bounds. Like that. And that's all. Yeah, something's wrong with my syntax there. Oh, x is still not here because that's for some reason called I. Tuple index out of range. A, B. Tuple index out of range. Where are we indexing tuple? Where are we indexing the tuple? 2, 3, 4, 5. 1, 2, 3, 4. There. So we have 1, 2, 3, 4, 5 placeholders, and for some reason we are only giving it 1, 2, 3, 4 variables. Okay, so I'm missing R here. All right, so here we go. Initial x naught is 0.5, and then oh, of course, I wanted to say the which iteration type that was before, so that we can see. Let's call this T. Type is a word which is special. How about now? Okay, Newton bisection. Wonderful. This is not very neat when that we have this axis not aligned properly. So let's try to align them. And since I'm working with dot format printout, we will add formatting after the after a column into this placeholders, the fields. So first I want to say 3D, which is going to give me 3 spaces for the iter count, and less will align it, if I remember correctly. Yeah, that's fine. Now for Newton and bisection takes how many spaces? When assigns 9. So let's just say 9s. So this will print the second field, which is T, type into nice 9 spaces. Let's take a double space here. Okay, x is going to be a float, so we can say 10f, and that would give it 10 points after the comma. 4, 5, 6, 7, 8, 9, 10. There we are. 15 maybe. The error I like to print, and let's do a double spacing. The error I like to put into this scientific notation so that we see the power of the 10. And then bounds, well, they can be 5 decimal digits, like so. Okay, now it's all nicely aligned. Newton bisection x error, we can see immediately what's going on, so we don't need the max iter anymore. And this is how, for the given values of a, b, and c, this is how the iterations go. It performs the Newton step with the new x being moved from 0.5 to 0.87, and then a bunch of bisections, okay, until we get to the point where Newton step is still fine. It doesn't take us outside of 0, 1. And so we make 2 Newton steps, but then the next Newton step apparently is taking us out of the interval again, and we're going back to bisections. Oh, that's very interesting. That's very interesting. Let's investigate a little bit more. So now, after a significant amount of time staring at the code, I think I've noticed the problem. And the problem is that we made a mistake in the derivative. Look, this is supposed to be the derivative of the function itself, so a divided by x, b divided by 1 minus x, but minus jumps out of the chain rule. Okay, let's look at this now. Okay, that's what I expected. I expected that the bisection may be helpful at some for some time. Let's add back the plot. So bisections are, we start at 0.5. We first arrive somewhere to 0.86. And here the Newton method points outside of the unit interval. And that's where bisections start helping. But then the function, turns down quite significantly. And this is where the Newton should be staying within the interval all the time. And so once we transfer to Newton iterations, it shouldn't ever go back out to bisections again. And therefore, what we had before was looking very strange. And of course, then the thought process is that the Newton method is making a mistake there. Well, the mistake is that we had the wrong derivative. And so the Newton method was not making the appropriate Newton step. It was doing something else. Okay, so here we are. I think this is about all that we need to do. Let's maybe try this for some other values of the parameters. And I want to see, to what extent can we push the solution to the edge. So if I make this C constant a really large one, okay, now the graph is incapable of making a complete line. We could actually add some points next to the next to 0 and 1, really close to each other. Well, let's not bother with that. But we can see that now the solution is something to the power of 10 to the minus 7, something times 10 to the power of minus 7. Let's actually print it. And let's give it many digits, but not in scientific notation. Yeah, many zeros here. Can we have more? How about now? Well, see, now the whole graph is just a straight line. In fact, it is still something like this, but all squished because of the scale. And as you can see, the solution is really close to 0, but still at some distance. And I guess I need to crank this up really, really high to move it even closer. Yeah, it's hardly visible. So the log really becomes vertical at that point. Okay, so do we need to do anything else? Iterate until convergence. Yep. Well, there you go. A nice combination of Newton and bisections. So again, the idea is that we are trying to make a Newton step which is more efficient, but if it doesn't work, then we fall back to a more robust method, namely the bisections. And as you can see, it converges every time, and becomes very robust and not very time-consuming still. Okay, see you next time.